In this video, we'll discuss what is probably the single most important hyperparameter in all of deep learning, the learning rate. The learning rate can easily make the difference between diverging and reaching state-of-the-art performance. Let's dive right in. Choosing the learning rate. So setting your learning rate is tricky. If you set it too large, then optimization diverges. And if you set it too small, then the optimization process actually takes forever. So this is a really crucial choice to get right. And we're going to start this video by looking at the different situations that can occur when you actually choose a learning rate in different ways. For this, we're going to use this visualization here, where on the x-axis, we have a single parameter, theta, and on the y-axis, we have f of theta. And of course, this is a massive oversimplification because we don't in practice only have one parameter, theta, but we have millions. But in one dimension, we can actually look at this. So the first case that I would like to look at is where you have a nice small learning rate that works quite well. So, and here we start at this point, we compute the gradient, we multiply that by the learning rate, subtract that from our current parameter value, and so we're moving in this direction and down here to this point. Then our gradient is smaller, so our next step is going to be smaller. We get here, and again here, 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 until we converge. So that's a nice case. We're making good progress and converge in the end. Now, with a very small learning rate, we still converge, but it can take very long because all the individual steps are much smaller. If we have a medium-sized learning rate, we can still converge, but we can actually shoot over the target. So the gradient is the same as we saw before, but we multiply that now by a larger learning rate. So we move all the way over here and then down there. And then from this side, again, we overshoot. From this side again, we overshoot. And we're kind of homing in on the target and still converge. But there's this zigzagging, we are overshooting all the time until we finally hit the goal. And now here's a case of a large learning rate where we can actually diverge. So let's say we're starting here, and because our learning rate is so large, we overshoot the target, and we overshoot the target by more than, so the target was here, and we actually go further away on the other side so that our function value actually gets worse. And then from this side, we now also overshoot, our function value gets worse. We overshoot again, our function value gets worse. And overshoot again, function value gets worse, and so on. So our function value gets worse and worse and worse, and we diverge. So notice that well, we're drawing these pretty pictures, and it looks very much like, well, all you need to do is to look at this plot, and then you see what's going on. But of course, well, this is again a one-dimensional plot, and in practice, we're actually optimizing in millions of dimensions. And you can't visualize this nicely. All that you can observe is that, well, our function values, in this case here, we started with this one, then we got 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 this one. So actually, over time, our function values are going up, and this is bad. We're diverging. In contrast, in this case here, we saw this function value, then we saw this one, then this one, then this one, and this one, and this one. And so we converge. And so that's actually the information that we can get, the function values over time. And so we usually plot this in relation to not time, but as a function of the number of epochs, where an epoch, as you recall, is an iteration in stochastic gradient descent over the entire data set. So we usually observe our loss on our training set, and we can also compute it on the validation set as a function of the number of epochs. And well, in practice, we might actually see learning curves such as these. And while some of these have a good learning rate and some have a high and some have a low, and since this is all you see in practice, it is actually useful to be able to look at them and say, it looks like my learning rate is too small or too large and so on. So because of that, I prepared this little learning rate quiz where you can actually stare a little bit at these curves and then think about which of these curves actually denotes a low learning rate, a high learning rate, a very high learning rate, and a good learning rate. All right, so please pause now and think about this. And now that you've thought about this, I will give you the answer. So this first case here, learning curve A, well, that's actually a case of divergence. And we've seen before that divergence happens with very high learning rates. And this is also the only one that really dramatically diverges here. So this is going to be the very high learning rate. The second one, B, we see that initially it actually makes progress the fastest. So that speaks for it being pretty large in areas where it's good to just go towards a general direction of the minimum. You actually want to go quite quickly. But when it actually comes down to properly getting to the bottom of the local minimum, then, well, actually lower learning rates are required. And we can actually see that this basically bottoms out here, and maybe there is an ever so slightly increase in the loss. And so it's really not making progress anymore. And that speaks for it being the high learning rate. Now this learning rate C here, and this curve is really slow. It makes the slowest progress in the beginning already. And well, it makes steady progress, but it's taking its sweet time. So this is then likely to be the low learning rate, and that makes sense. D is the good learning rate, and that also achieves the best performance, that has reasonable performance in the beginning here and keeps on making progress in the end. All right, so from this you can see already a first glimpse of what you're in for when you actually diagnose learning rates in practice. What you also should have seen from this is that, well, actually it's kind of annoying to be bound to have a fixed learning rate, because even this good learning rate here wasn't the fastest in the beginning. And in fact, there's a theoretical result that with a fixed learning rate, alpha, SGD will actually never settle. So even this good learning rate here, well, this will not get down to the optimum. Actually, this lower learning rate, C here, will get lower at some point in the far future because, well, it's just very slow. But at some point, it will actually go lower. And, well, actually, the sufficient condition for SGD to converge, so in the limit really get to the minimum, is that, well, there's two parts of this condition. The first part is that the sum over your learning rates from k equals 1 to infinity is infinite. And the second condition is, the second part of the condition is that the sum of the squared learning rates is smaller than infinity. And actually, this can be achieved, for example, by setting the learning rate to 1 over k for the kth epoch. Now, it would be nice if things were as easy in practice, just use that learning rate schedule, but in practice that is actually not being used, because in practice people don't care so much about this limit of infinitely many samples, many updates, many epochs, but people have limited amounts of time. And so rather, people use some other standard learning rate schedules in practice. The first one that is quite popular is this linear decay, where you simply have a learning rate at time step k that interpolates from an initial learning rate to the final learning rate that you're going to use henceforth. The second one is an exponential decay. This is actually a bit more popular, where your learning rate at time step k is your learning rate at time step k minus 1 times the multiplicative factor beta, with beta being smaller than 1. And so this exponentially goes down. You can also rewrite this as alpha k being b to the power of k times your initial learning rate. And so you see that at each time step, this is actually going down by a multiplicative factor. And so it goes down much faster than the linear k, for example, in the beginning. And in the end, well, you don't see this, but it's still moving down here. You don't see it with a non-log scale, but it's continuously going down until the end, whereas this one here, the linear one, stays constant. Another popular learning rate schedule is the so-called step decay, where you actually keep the learning rate constant for a while, for example, n epochs, and then you decay it by a multiplicative factor. For example, you divide it by a factor of 10, and then you keep it constant again for n epochs, and then you divide it by the same constant of 10, keep it, divide by 10, keep it. And well, this also allows you to be a little adaptive. You can also make this decision to divide by a factor of 10, not only every n epochs, but you can also diagnose whether you're still making progress or not. You can look at the performance over time and can see whether, for example, your curve is slowing down, and then you can divide your learning rate, and typically then you get another improvement like this. And so the green here, what I'm plotting is f of theta at epoch k. All right, and the final learning rate schedule that I'd like to mention is cosine decay, which also starts from an initial learning rate and then, well, applies this formula here where you know the total number of epochs n that you want to invest for your schedule. At this epoch number 10, you're actually going to have a learning rate of 0 because you have k divided by n. That's going to be 1 times pi. Cosine of pi is minus 1. 1 plus minus 1 is 0, so you're going to have a learning rate of 0 at that time. And you're going to start at a learning rate of alpha 0 because the cosine of 0 is just 1. 1 plus 1 is 2 times a half is 1. So 1 times alpha 0, that's where you start. And then you go down with this cosine schedule. And this cosine schedule is notably in the beginning, it actually goes down slower than a linear decay. And in the end, it actually also goes slower. And in between, it goes a little bit faster. And with respect to cosine decay, or also called cosine annealing, I'm a little bit biased because, well, I'm actually a co-author of the paper introducing it. But I would nevertheless like to say that for a lot of different data sets in computer vision, object recognition, and so on, really in order to get state-of-the-art performance for this, you kind of have to use cosine annealing. Now, a final learning rate schedule that I would like to mention is actually from the same paper by my previous postdoc, Ilya Loshilov, and me. That's called SGD with warm restarts, SGDR. And this uses iterative stages of convergence by a very aggressive learning rate schedule. So you quickly cool down your learning rate to 0 to converge to an okay solution, and then you heat up the learning rate again and then cool down your learning rate more slowly again to converge to a better solution. And then you iterate that. And when you restart the learning rate, so when you heat it up again, then you keep the weights just like in any other learning rate schedule. So you don't reinitialize your weights or anything. And in pictures, this looks as follows. So notice that here we have the learning rate, and here we have the epochs, and the learning rate is plotted on a log scale. So we start with an initial learning rate, and then very quickly drop this down to 0 with cosine annealing. And then we heat it up again, and then drop it down to the next 0, and heat it up, and drop it down to the next 0. And notice that, well, these stages of convergence get larger over time. So you have more time to converge, and that typically leads to converging to better and better solutions over time. And here, this learning rate schedule is compared to a step decay. And the types of results you get with this are as follows. So with a step decay, this here is similar to the curve I plotted before, where you kind of start to settle, then you reduce the learning rate. So that's this point here. Then you quickly improve. Then you divide the learning rate again, you quickly improve, and then there is another imperceptible improvement here. In contrast to that, SGDR actually makes progress much faster because it cools down the learning rate much faster. So here it already has this performance, but then, well, the learning rate is already down at 0 and you don't make progress anymore. So that's why you then actually heat up the learning rate again to here and cool down again to the next point. And since you have more time to cool down in between, you actually move to a better point and to a yet better point in the next stage of convergence and to a yet better point. Now, one nice thing about this is that, well, you can actually have these snapshots at each of these stages of convergence, and each of these actually gives you a neural network, and that is what you would return if interrupted in between. So for example, if you have to return some network at this point here where you haven't converged yet after reheating, then actually what you would return is the network at the previous state of convergence. So in fact, this snapshot of your neural network. And when you, so this is with cosine annealing, so you might actually ask, well, here we're comparing to the step decay, but well, since cosine annealing is a part of SGDR, why don't we compare to cosine annealing? And well, that is what we do in this plot here. And here now, well, here we plotted for the points to be returned. So for the snapshots, so if we have to return at this point, we just return the snapshot. That's why we have these constant regions of performance. Here in this plot, for all the intermediate points, we're plotting the performance of the partially trained network, because otherwise for cosine, for the single cosine, we couldn't plot anything. So for that is the natural thing to plot typically. So also, for example, for the step decay, you have to plot whatever you have at that particular point in time, and you just don't have any fully trained or partially converged networks, you don't have any snapshots in those cases because you don't have iterative stages of convergence. But for SGDR, we actually do have these iterative stages of convergence, so we can remember these snapshots. And so we see here, compared to a single cosine decay for the entire budget, we can actually achieve very quickly very good performance. So within less than 100 epochs, we can actually achieve the same performance as a single cosine decay would get with something like 1500 epochs. So that's a substantial speed up. But of course, in practice, you also want to get the last bit of performance, and it would be sad if we would stick at this poor performance. So poor is relatively good, but it's not the best. So, but in the iterative stages of convergence, this gets better and better. And so in the end, you also get something that's as good as the final result of a single cosine decay. And one other thing that's very nice about this SGDR is that you can use these snapshots in order to actually build an ensemble of neural networks. So if we have to return at anywhere after this point here, we could actually return an ensemble of these 4 neural networks that we get for the cost of training, well, a single training. In terms of memory, we still have to save 4 different networks, but in terms of training cost, it's the same cost as running a single optimization of step decay or a single optimization of cosine annealing and so on. So in a sense, we get ensembles for free. And in practice, actually these ensembles have given us improvements in terms of the error rates of between 10 and 20% in terms of relative error. So that can actually sometimes be a very substantial gain compared to other tunings of your learning rate or your momentum or other hyperparameters. All right, one final thing that I would like to mention where this anytime performance of SGDR comes in handy is that, well, it can tell you very quickly whether everything is going okay with your optimization trace. So whether you have chosen your architecture in a meaningful way, whether you've chosen your hyperparameters in a meaningful way. And it can tell you that quickly because, well, very early on, you get this good performance. Whereas it's very hard to tell, for example, from the step decay, or also from a single cosine annealing, where this is going to go in the end. Will this achieve 4% error? Will this achieve 3% error? Will it achieve 2.5% error? That's very hard to tell. Whereas in SGDR, well, after 100 epochs, you already have an upper bound on where it's going to go. And in this case here, you already have 4% error. So it's not going to get worse than that. So in order to do rapid prototyping and so on, it's very helpful to get that anytime feedback. All right, that's all I wanted to say for SGDR and learning rate schedules. So this brings us to the end of this video. And as always, I'd like to leave you with some questions. And I encourage you to pause the video here and think about them to activate the material. Thank you, and I'll see you in the next video.